So now the next question that we have is, we take this x of nts, pass it through something, okay. This is the analog quantizer. No, this is the amplitude quantizer.
Amplitude quantizer.
Sorry, amplitude quantizer. Quantizer, yes. And we want to get xq of nts. Okay, so this so effectively x of nts is any real number, right?
Yes.
Or I will say maybe positive real number, because it's a voltage and all that, and this is going to come out to be some integer. Okay,
yes, correct.
Positive integer. This is a, we can assume
Yes.
this mapping.
Yes.
Okay, last time we saw I think 130 levels, 0 to
Correct.
129 or something like that.
That's right.
So now how do you think we can go about doing this?
Okay. So, I basically have some voltage, right?
Yes.
So, I am thinking back to what we did when we discussed this.
Yeah. So we had xq
Yes.
versus x,
Versus x.
right? And we said any analog voltage that is between 0 and delta
Yes.
will get approximated by 0,
By 0 and
right?
correct.
The lower value, anything between delta and 2 delta
Correct.
will get approximated by
Correct.
1, then 2, then 3, 4, like this. We just went all the way,
Correct.
right? You got a staircase waveform all the way, and then it would saturate.
Correct.
Okay.
That's right.
So now how do we go ahead and implement such a circuit?
Okay. So, what I need to do,
Yes.
I have my x value.
Yeah.
So, for each and every x value, I need to come back to this graph,
Yeah.
find out what value corresponds to that,
Yes.
and output that.
Yes.
Right? That's what I want
Correct.
to do.
So mathematically, what does the staircase basically mean? If x is between n minus 1 delta, okay,
Yes.
by the way, this is the delta that we spoke about,
Yes.
okay, and n delta,
Yes.
right? Then we wanted this to be n minus 1.
Correct.
Is that correct?
I think that is correct.
Therefore, between 0 and delta it is delta.
Correct.
Between delta and 2 delta it is 1. Between 2 delta and 3 delta it's 2
and
so
so
on.
on. Correct.
Right?
Correct.
And if x
So, you will count from 0 to n minus 1?
0 to n minus 1.
0 to n minus
n
1.
minus 1. Right? And if anything that is greater than the max value,
Yes.
okay, let me just call that x max. Right? This is what we call here x max. Anything that is beyond x max is going to get approximated to, so maybe I should not use capital N here, let me use small n,
Sure.
okay,
Yes.
because I want 0, 1, 2, 3, 4 all the way to n, this is n minus 1.
Yes.
Okay.
So capital
it
N
will get approximated to n minus 1, and anything below 0, right? If
Yes.
it happens to be x less than 0,
It will just be 0.
it will simply be 0.
Okay.
Okay. This is the mathematical function that we want to implement. Now,
Sure.
what is the best circuit that we can actually implement?
Okay. So, I'm thinking before we implement the circuit, I'm thinking in my mind how I would do it.
Yeah.
So, one way to do it, which will take a long time, is I start looking at each value, comparing.
Yeah.
I
Yes.
start comparing. I start from 0,
Yes.
compare it,
Yes.
right? See if it is higher or lower.
Lower.
Go to 1,
Yes.
higher or lower, and so on. Until
Exactly.
I'll hit the value for which it
Correct.
is working.
Correct.
But that seems like very tedious.
Yeah, and that also seems like a very computer science approach.
Computer science
right?
approach
It
to
seems
it.
like searching in
Algorithmic
an array.
searching in an
right?
array,
Yeah.
right? So, see, now I'll go the other way.
Yes.
Brute force, this is one brute force method.
Yeah.
The other extreme of the brute force method, I can imagine, is doing, what I was doing first is comparing with each and
Yeah.
successively.
Yeah.
Maybe I can just compare with all of them in one go.
all of them in one go.
Yes.
Right.
So I'm going to do comparison. I mean, a computer can do so many things in
Yes.
parallel.
Yes.
I cannot.
Yeah.
Right. But a computer can.
Yeah.
So I'm imagining that I can just compare with each. I can, there are n-1 equations or n
Yes.
equations here.
Yeah.
I can do those n equations,
Right.
n comparisons
Exactly.
instantaneously.
Great. So you made a point that you want to compare against all of them.
Yes.
Yes. What does all of them mean here?
So I need to compare with each and every n deltas.
Yes. Right. So assuming that this is a voltage.
Small n delta.
Yeah. I'm going. You want to compare with 0, delta,
Delta, correct.
2 delta, 3 delta.
Yes.
All the way up to what?
N minus 1 delta.
Delta.
Correct.
Okay. So before we go ahead and see, okay, how to do this comparison, is there a way to generate these voltages with what we have already studied?
Okay. Yes, we have. We have seen mixing circuits,
Yes.
which can do this,
Exactly.
right?
Exactly.
Because mixing circuits can give you any intermediate voltage.
Right? Yeah. So in fact, if you look at this, you take the X max voltage.
Yes.
Right? And simply build a resistive divider.
Yes.
Right? All the way down, you put n resistors there.
Yes.
Right? Out here, this, so X max, right? This is X max, you have n resistors,
All of them equal.
all of them equal. Okay, this is
Okay.
R. So you will simply get delta over the next resistor, you will get 2 delta, 3 delta, right? 4 delta, okay, and 5 delta. Here we have shown it only for some say 5 levels,
Sure.
right? And what is delta? It is equal to X max voltage divided by 1, 2, 3, 4, 5, 6.
6R.
6R.
So this is the current,
Yes.
right? And now this, I will need to multiply this with the resistor R
Yes.
to give delta.
Oh, you're saying, okay, how to solve this?
Solve
Yes.
this, yes.
So you assume that the current is I through
Okay.
each of this.
Okay.
That means X max
By 6R would be the current.
by 6R, exactly.
Is the current.
Right, is the I, okay.
And you multiply that.
By how many ever resistors
Resistors
it
are
goes
there.
through, right?
I see,
Since the
okay.
last one goes through one resistor,
Okay.
it is going to be I into R.
Yes. So it will be X max by 6 will be the delta.
Exactly.
Not
So-
X max by, I think you need to rub that R.
Correct.
X max by 6.
6.
Perfect.
Okay, so delta is X max by 6,
6.
and 2 delta, so here you will get X max by 6, you will get X max by 3,
Perfect.
and so on.
So on.
So what we have done is we have generated a set of voltages with which we have to compare.
We have to compare.
Okay.
Okay.
Now how do we compare?
Okay. So we don't know how to do comparison yet.
Yes. So interestingly, Bobby and myself in an earlier lecture did introduce the students to the concept of an amplifier, because we said that you have to go through, if you have to send the output, sound output to a large power amplifier, you have to amplify it,
Sure.
right? And we
Yes.
also demonstrated the idea of saturation. What happens if your amplification is too high and delta, just by conservation of energy, it has to sort of saturate.
Yes.
Okay. So we did introduce the students to the concept of an amplifier, though we did not call it a differential amplifier at that point.
Okay.
Right. So we said V1, V plus, V minus, output Y, okay, is some A times V plus minus V minus. Okay. Let me put this as a subscript carefully, because okay. So the two voltages are on the positive and negative terminals, and if this amplification factor is high enough, right?
Sure.
You cannot just get 1000 volts out of this, right?
It will just saturate out.
So it is going to be driven or controlled by plus VDD and let's say minus VDD, right? So if V plus is greater than V minus, even little bit, and the amplification factor is high enough, this comparator would simply give 1,
One.
right? Or let's call it VDD. So the
Interesting. So if you have an amplifier with high enough gain,
yeah,
which has this characteristic with A being very large, it will look like a circuit. So you called it a comparator.
I called it a comparator
Because
right?
it's performing comparison.
Exactly, right?
Perfect.
So if V plus greater than V minus implies Y equals VDD, okay? And if V minus greater than V plus, this amplifier will just return minus VDD.
Maybe we should also show the characteristics, input-output characteristics on a plot.
Yeah.
Sometimes that helps.
Yes.
So maybe we'll just plot Y as
Okay.
a function of V plus minus V minus.
Okay. So this is V plus minus V minus.
Yes.
Okay. And this is the output.
Okay.
Right. So if you look at, if V plus is greater than V minus, we are saying, assuming A is very large.
A is very large, correct.
Okay. It would be something like this
Plus VDD.
plus VDD. Okay. Likewise, if it was other way around, it would be like this.
Minus VDD.
Minus VDD. Okay.
Perfect.
So this, and
Nice.
if it is not ideal, then there would be like some small linear portion
Yes.
like this.
Yes.
Okay, that's what will happen, but let's not worry about that for now.
Yeah.
Okay, so we are going to assume an ideal comparator. So now what do? So we have the x of n TS,
Yes.
right, available with us, which has been sampled and held, and now I want to get out this integer that corresponds to this staircase waveform.
Okay. So I already said that
Yeah.
one possible way to go is to compare everything in one go.
In one go.
Together.
Yes. Okay.
So which means
Okay.
I will take each one of these delta, 2 delta, 3 delta, 4 delta, etc.
Yes.
I will compare that with x of t, or
Yeah.
actually x of nts,
Yes.
right?
Yes.
At any,
Yes.
with each and every one of these,
Yeah.
I'll get a whole bunch of outputs.
Yes.
So I'll
Okay.
actually need, if I have capital N minus capital N levels,
Yeah.
or capital N minus 1 levels,
Yes.
I'll need N minus 1 comparators.
Exactly.
Okay.
Okay. So let's do that. Okay. So what we are saying is we are going to say plus minus. Okay. Plus minus. Okay. And maybe we can even draw the resistor values right here.
Yeah.
Okay. This is one resistor, second resistor. Okay, like this I have, you said n minus 1 comparators.
So maybe we'll just do it with 3 levels. Maybe that's the easiest to show, right?
Okay, we'll
just
do
do
it
4
with-
resistors,
yes.
3 levels?
Yes, we'll do it
to
with
compare
4
with?
levels. Yes, okay. So that way we can draw all the comparators.
Yes.
Okay. So 4 levels and 3 comparators, right?
Yes.
Okay. So then therefore
4 resistors, 3 levels, 3 comparators, correct?
yes. Okay. I have this one. Yeah. Okay. This is my X max.
Correct?
So all I have to do is tap each point of the
Yes.
resistor like that to the negative end of the comparator, because we are
Right.
comparing against them.
Correct.
Right. And all the positive ends are going to be shorted like this. Okay. I'll put the dots here.
To show that, okay.
Yeah, X of NTS.
Perfect.
Okay. And what you get now is each comparator, by the way, is going to just give us plus VDD or minus VDD, right? Or in some sense, I can call this state 1, state 0. That's all. Okay.
Okay.
Abstractly, you can just assume that this is, you will get. So for example,
Maybe we can put in numbers.
we can put in numbers. Exactly. Okay. So let us take.
I think it might be easy in this case.
Yeah.
Let us say X max is 4 volts.
4 volts. Okay.
Right.
So therefore, the delta is going to be what? 1 volt.
1 volt.
Right. Exactly.
Correct.
So here you will have 1 volt,
Yes.
2 volt, 3 volt.
Correct. Perfect.
Now what do we want? If anything is above 1 volt, if it is below 1 volt first of all,
Yes.
it must be 0.
Yes.
Okay, that's so we'll just plot the transfer characteristics also here. Okay, X versus XQ.
Yes.
I can remove the time from this. It's like
Yes.
a DC voltage.
It's like a DC voltage.
Okay, so I have delta, 2 delta, 3 delta and 4 delta.
Yes.
Right, so you're going to have 0. This is my waveform that I want. Right?
Yes.
So 0, 1, so this is code 0, 1, 2, 3.
Yes.
Okay? This is the integer mapping that we want. So
Yes.
if our x of NTS happens to be, let's say hypothetically 2.75 volt,
Okay.
right? So this is 1 volt, 2 volt, 3 volt and 4 volt. So 2.75 is somewhere here. So the answer that we are looking for is 2.
Is 2.
Is 2. Okay. So I'll write this in red, 2.75 volt.
Yes.
Okay. Now 2.75 will be compared against 1 volt.
Yes.
It is greater.
It is
You will get
greater.
an output 1.
1.
2.75 is greater than 2 volt. You will
Yes.
get an output 1. 2.75 is less than 3 volt.
Yes.
You will get 0.
0.
Right.
Okay.
Now how do I get this number 2?
So, it looks like, because I am comparing with whole bunch of voltages,
Yes.
I noticed that when we compared with 1 and 2, it gave 1s.
Yes.
So, it looks like when I compare, there will be a whole bunch of, when I start from the bottom and
Yes.
go to the top, there will be a whole bunch of 1s,
Ones.
which is plus VDDs.
Yes.
And then at some point of time, it will become
Switch.
0,
Exactly.
switch to 0 and then continue there, minus
Yes,
VDD.
exactly.
Right? So, the transition point tells me what that number should be.
Exactly.
So, in fact, in this case, let me put it this way. It seems like if I count the number of ones,
Exactly.
right, that gives me an idea.
It gives you then the bin actually where the bin is going to fall. So
Correct.
all you have to do is put some circuit. Okay. So actually this one, as you said, is VDD. Okay, some voltage, let's say 5 volt and minus 5 volt.
Yes.
Right. So it's like 5 volt, 5 volt, minus 5 volt.
Yes.
All you have to do is you have to somehow count this, right? Addition.
Yes.
And you will get an integer,
Yes.
which is xq of NTS.
Yes.
Okay. So you just mentioned earlier, right? We are basically comparing everything in one shot. So the name of such a quantizer is called a flash.
I
ADC.
see. Okay. A
Okay,
flash
because
ADC.
it does it in a flash.
In a flash.
Essentially, right? So that sort of makes it a very popular ADC, and it's probably the simplest thing to understand conceptually, right? So the ADC, as we saw, is sort of a very integral part of any sensing engine. Anything that analog has to come into a computer, you have to first meet an ADC, right? And an ADC does this, okay? And of course, now the question is, how long does this ADC take for it to sort of evaluate? When can I give the next input
Okay.
to this, right? So I mean, we say a flash, but it technically will take some time,
Sure.
right? So there are certain intricacies in which, of when you can sort of give the next one, but again, all that is related to the sampling time. If the sampling time is relaxed enough compared to the speed at which this ADC operates and all that, there will be no problem, right? You will get the answer very nicely. And so we have even now shown how we can get the quantized version, right? Time quantized, amplitude quantized version of this
Yes.
of this signal.
Perfect.
Okay. So the next thing to do is to actually dive into the digital computer, because
Yes.
so I have one question, right? So you said that this capacitor, right? The capacitor stores data,
Yes.
right? It stores some information. If you store a voltage V, right? And it's not connected to anything else, it just stores it forever. So
Yes.
can I use this as a storage element to store a voltage?
So, you can,
Yeah.
But you know, there will, if it's an ideal capacitor, it seems like the ideal storage element.
Correct.
But I can imagine that there will be some path through which charge might not stay for a long time, right?
Exactly.
If I wait long enough, charge, it seems like there will be some way.
Exactly.
In which
So,
charge will die out.
even here, if you just take this ideal switch that we said, right?
Yes.
We said that the ideal switch had an off resistance of mega ohms.
Yes.
Right? So, if you look at so this also is in some sense an RC circuit,
Yes.
okay, with mega ohms of resistance and whatever value of capacitor. So, effectively, if this happens to be connected to ground, then this guy will discharge
Sure.
at a time constant, which is this mega ohm into the capacitor value, right? So, therefore, the analog storage is not
Really not going to happen.
that easy.
Not
So,
that easy.
when we saw on the computer that Audacity basically stored the waveforms, did something with it, right? The storage is not in this analog manner,
Sure.
right?
Sure.
So, we will look at how that has to be stored, right? And even now, I think I'd like to remind the students, we have only looked at an analog to discrete amplitude converter. We have not looked at the analog to digital converter. We have not even mentioned what digital is.
That's true.
As yet, okay? Which we will do in the coming weeks. Thank you.
Thank you.